Right, so this video is going to focus on periodic trends. Periodic trends describe relationships among different characteristics between elements going across periods and going down families. When we are examining a period of elements, the valence electrons are being placed in the same outermost energy level. So it's going to be the nuclear charge, that there are more protons as we move across a period on the periodic table, that are going to result in reducing any shielding from valence electrons, from those inner core electrons, in terms of determining how these trends proceed. So when you're dealing with looking at a set of elements going across a period, you want to take a look at the number of protons that are present in those elements. More protons means more positive charge, and that means more attraction for those outermost valence electrons. When we're going down a family, we are increasing our nuclear charge, but we're also increasing our shielding. And shielding is going to have the more significant impact on your trends. Shielding comes about from filled energy levels, known as core electrons, that basically are in the path between that positive nucleus and those valence electrons. And the more of that shielding that you have, the more the protons, that nuclear charge, is being deflected by that shielding and is not going to have as strong of a hold on those outermost valence electrons. So some trends we're going to look at first is radius. Radius is just like it is in math class, the distance between the center of the atom to the out point of the atom. And when we look at the size of our atoms, we tend to see going across a period that their radii get smaller, and going down a family, their radii get bigger. As we're going across a period, we're increasing our nuclear charge. Those positive protons are going to hold on to the valence electrons more tightly. They're going to be more attracted to them because all of those valence electrons are in the same energy level. So there's roughly the same distance. It's going to be a little bit smaller, but they're roughly in the same general location compared to the nucleus. When you're going down your groups, however, you're adding on filled energy levels, which shield or deflect that nuclear charge from the valence electrons. And because they are not able to hold on to those valence electrons as tightly, they're not as attracted to them, the valence electrons can distance themselves more from that positive nucleus. So we see that going down a group, our radius gets larger, going across a period, our radius gets smaller. Ionization energy is the amount of energy it takes to remove an electron from an atom or an ion. This is going to be an input of energy. It's an endothermic change. Energy has to be added to remove these electrons. When we're looking at a period, we see that the ionization energy levels increase going across, generally speaking, and they decrease going down. Why is that the case? Let me talk a little bit about this first, and then I'll show you the graph where you see those relationships. The first ionization energy is forming a positive ion from an atom, removing a single negative electron, leaving you with a +1 charge. The second ionization energy would be removing the second electron, so that would be taking an ion from +1 to +2. Generally speaking, as I said, the ionization energy values increase going across a period and decrease going down. As you increase your positive protons, as you increase your nuclear charge going across a group, it's going to be able to hold on to those valence electrons. It's going to be more strongly attracted to those valence electrons, and more energy is going to be required to remove one of those electrons because of that increased attraction. When we're going down a group, because the attraction for the nucleus for those valence electrons has been decreased, the distance is going to be greater, and that's going to allow less energy to be needed to remove any of those valence electrons, since the nucleus is not holding on to them as tightly. There are some notable exceptions, and it has to do with stability. If you have an atom or an ion with either a filled energy level or a filled sublevel, like a filled S sublevel, or even a half-filled sublevel, which we could see with S and P, those are pretty stable formats for electrons to be placed in. Those are pretty stable orientations. And so when you have one of those, more energy is going to be needed to remove an electron from that stable state. So here we see, again, going across our periods, generally speaking, those ionization energy values are increasing, and going down a group, we see that they are decreasing. I do want you to notice that with beryllium to boron, we see kind of a drop in those ionization energies, and that would be because when boron gives up that one electron, it now has a filled sublevel. It goes to having the configuration similar to beryllium. We see the same thing with oxygen. When oxygen loses an electron, it gets to have this configuration that's similar to nitrogen, which would be half-filled for its p sublevel. You will notice that that group containing nitrogen and that group containing beryllium are going to require more energy to remove an electron from than the one that comes after. That would be in part because they are in some of those stable conformations, whether they be a filled sublevel or a partially filled sublevel. Electron affinity is a little bit different than ionization energy, and that ionization energy is the energy required in endothermic change to remove an electron. Electron affinity is the amount of energy that is released when an electron is added to an atom. And the trend follows the same pattern. It tends to increase going across a period and decrease going down a family. As you're going across a period, as you increase your nuclear charge, the nucleus is more strongly attracted to those outermost electrons, and it's able to knows how many orbitals have empty places for electrons. As you get closer to filling that valence level, that valence sublevel, and getting your complete shell of electrons, more and more energy would be released to grab onto those outermost electrons. As you go down a family, because you're having more shielding, you're going to reduce the attraction of the nucleus for those valence electrons. They're going to get further separated, and as you continue to add more shielding, less and less energy would be released because the nucleus is not nearly as attracted to those valence electrons with the increased distance. And so there you see an example of that trend. And again, there are exceptions. Also has to do with stability with the half-filled sublevels or the partially filled sublevel, or sorry, the completely filled sublevel, like with S. The last trend we're going to talk about today is dealing with radius. And we did talk about radius earlier, but right now we're going to look at ionic radius. When we are looking at ionic radius, we're going to be comparing the radius of these ions to their parent atoms. And what you see with the blue atoms or the blue ions is that they are all positively charged. What that means is that they have lost one or more electrons. You have the same number of protons, but because you have a reduced number of electrons, the nucleus is able to hold on to the remaining electrons even more tightly, causing their radii to get smaller. With the orange and green atoms, we see that the ions are actually larger than their parent atom. As you form negative ions, you have gained electrons, so now you have more negative electrons that those positive protons are trying to be attracted to. And if you increase those number of electrons, you are basically diluting the strength of that nucleus. You're reducing the attraction of the nucleus for individual electrons because it has to be spread out across all of the electrons. So your anions are going to become larger than their parent atoms. Your cations are going to become smaller than their parent atoms. Isoelectronic ions are ions throughout the periodic table that have the same number of electrons. So these 5 all have, make sure I've done my math right, yeah, 10 electrons. O2 minus, O has 8 electrons, you add 2 to it to get 10. F minus had 9, add 1 to it to get 10. Sodium had 11, subtract 1 from it to get 10. Magnesium had 12, subtract 2 to get 10. And aluminum had 13, subtract 3 from it to get 10. All of these have the same number of electrons, but because they are different elements, they have different numbers of protons. If they have more protons, they're able to hold on to their electrons more tightly and they would become smaller. If they have fewer protons, they would have less attraction for those additional electrons, and those particular ions would get larger. So when you are isoelectronic, the fewer protons you have, the larger you get, which would be the case of O2 minus. And the more protons you have, the smaller you would get because the more attraction you would have for that number of electrons, which would be the case with aluminum. So here are some examples. We're going to rank these based on size. So we're going to find them on the table. Rb is number 37, sodium's number 11, beryllium's number 4. If you are increasing in size, you're going from smallest to largest. Remember, we get larger going down a group and smaller going across. So there's more shielding present with rubidium. So that would be my largest atom of these 3. Beryllium is in period 2. So it would have the least amount of shielding. Although they are not all in the same group, relatively speaking, beryllium would have, because it has less shielding, is going to be relatively smaller than sodium. So beryllium, then sodium, and then rubidium would be my order for size. Strontium's number 38, selenium's 34, neon's number 10. They're all in different periods. They're all in different groups. The one with the most shielding is strontium. The one with the least amount of shielding is neon. Neon is at the very end of my period, so it would be the smallest within its period. Selenium is 2 down from it, so it has a filled layer of core electrons separating its nucleus from its valence electrons, so selenium would fall in between. Fe is number 26, phosphorus is number 15, O is number 8. Again, more shielding would be present with Fe. The least amount of shielding would be present with O. Phosphorus would fall in between. Now, I believe we're going to look at those same set of examples, but this time with ionization energy. Remember, ionization energy is the willingness to give up an electron. And if we are increasing in ionization energy, we're going to require less energy to remove an electron than we are if we're going to require less energy to remove an electron. Sorry. So rubidium again, 37. Sodium again, number 11. Beryllium again, number 4. As you get further away from your nucleus, you require less energy because there's less of an attraction for those electrons. So the one with the smallest ionization energy would be rubidium. The one that has its valence electrons closest to the nucleus would have the greatest ionization energy, which would be beryllium. Sodium would fall in between. Strontium's number 38, selenium's 34, neon is number 10. Again, the one with the greatest amount of shielding is going to have the smallest ionization energy, has the least attraction for its valence electrons, and that would be the case with strontium. The one with the most attraction for its valence electrons would be neon. Period 2, selenium, and period 4 would fall between the two. Fe 26, phosphorus 15, O is 8. Fe would have the most shielding, O would have the least shielding. So O would require the most ionization energy to remove an electron. Fe would require the least. Also keep in mind with O and P that as you move across a period, the ionization energy levels are going to increase. And as you go down a group, your ionization energy levels are going to decrease. So even if we look at it from the nuclear charge perspective, O is going to have a more increased nuclear charge within its period. And then phosphorus, although it's one shy, has that extra layer of electrons, that shielding, that is going to cause its ionization energy to be a little bit less than oxygen's. So order these atoms from least exothermic electron affinity to the most. Remember, electron affinity by definition is exothermic. So N, O, and F are in the same period. The one that least wants to gain an electron is going to be the one with the smallest nuclear charge, and that would be nitrogen. It has 7 protons compared to fluorine, which has 9. So those are in order. And then if I look at bromine, chlorine, and fluorine in group 17, shielding is going to determine this trend. And so the one that has the least exothermic electron affinity is going to be the one with the greatest separation from its nucleus, which would be bromine. Fluorine, having the smallest amount of shielding, would be the one with its electrons closest to the nucleus and would have the greatest electron affinity. Chlorine would fall in between. Here you're given electron affinities for aluminum, phosphorus, make sure I've got these right, aluminum, silicon, phosphorus, sulfur, and chlorine. We see that aluminum and silicon, it increases in electron affinities, but then it drops for phosphorus and goes back up for sulfur and chlorine. Why would that happen? Electron affinity is the ability to gain an electron. And if we remember with phosphorus, if it's gaining an electron, it's forming a negative ion. Phosphorus started with 3p electrons. It already had its 3s electrons, so it had a half-filled sublevel. Every orbital had 1 valence electron. P minus now has 2 electrons in one of its orbitals, and then the other 2 only have 1. So they're no longer in balance, and that's going to cause your configuration to change from a more stable half-filled sublevel to no longer, to not as stable. It will eventually get there, but 3p3, by having the electrons evenly distributed, is just a little bit more stable than 3p4. So you're going to need to, you're going to have less energy given off to have that jump from 3p3 to 3p4. Here we're looking at ions of chlorine, Cl minus 2, Cl plus 2, Cl minus 1, Cl plus 1, and then an atom of chlorine. So they all have the same nuclear charge, they all have the same number of protons, but they have different numbers of electrons. More electrons for the same number of protons is going to disperse that attraction, is going to allow the valence electrons to have more separation from the nucleus. Fewer electrons is going to allow the nucleus to hold on to those that remain more tightly and cause your atoms be more attracted to those electrons and cause your atoms to become smaller. So the one that is the smallest would be the most positive charge, which would be Cl plus 2. The one that is the largest would be the one with the most negative charge, since they all have the same number of protons, and that would be Cl minus 2. Three ions that are isoelectronic with argon. So if I'm asked a question like this, I first find out how many electrons argon has, which is 18, and then I want to make ions on other sides of argon that also have 18 electrons. So there are just some examples of ions. Chlorine has 17 protons and 17 electrons. By gaining one, it has 18 electrons. It's isoelectronic now with argon. S2 minus had 16, adding 2 gives it 18 electrons. Phosphorus had 15 electrons, having a negative 3 charge gives it 3, also 18. Potassium had 19 electrons. By losing one, it goes to 18. Calcium had 20, losing 2 gives it 18. Scandium had 21, losing 3 also gives it 18. You could pick any ions you want as long as they are going to have the same number of electrons. I will tell you that your charges, I have personally never seen a charge, negatively speaking, go beyond -3, and I have only seen positive charges go above +3 for transition metals and for the more heavier metals like lead and tin. So try to keep, if you were asked a question like this, your charges between -3 and +3. If these all have the same number of electrons, the nuclear charge is going to determine which ones are smaller and which ones are larger. The more protons you have for electrons, the greater the attraction the protons will have for those electrons, which will allow those ions to be smaller. And so that would be with your more positive ions. So scandium would be one of your smallest. And then the ones that are larger are going to have more electrons and not as many protons, so they're not going to be able to be as attracted to them. So your more negative isoelectronic ions are going to be larger. So in order, we would go from scandium to calcium to potassium, then our neutral atom argon, and then our negatively charged ions from smallest to largest, chlorine minus, S2 minus, and P3 minus. Why does rubidium have a larger radii than Na? Na and Rb are in the same group, but Rb has more shielding than Na. Rb has more filled energy levels than sodium. They both have the same number of valence electrons. Rubidium definitely has more protons, but it has all these filled energy levels that are separating its positive charge from those valence electrons. So because of those additional energy levels, the protons that rubidium has are shielded from that valence electron, weakening the attraction between the nucleus and those valence electrons and increasing the separation between the nucleus and rubidium's valence electron. So when you are asked to answer questions like this, you need to make sure you distinguish between any physical differences between the two elements, what those differences have to do with our trends, and then how that difference with our trend relates back to the specific trend that you are exploring. Here we want to know why aluminum has a bigger radius than Ar. Aluminum is in the same period as argon, so they both have the same number of filled core electrons, but aluminum has fewer protons than argon. Argon has 18, aluminum has 13. So argon has a greater nuclear charge, and it can hold on to its 18 electrons as a result. It's more attracted to them than aluminum's 13 protons are to its 13 electrons. The increased nuclear charge, having more protons, strengthens argon's attraction for its valence electrons, or if you were going to look at it from aluminum's side, the decreased effective nuclear charge weakens aluminum's attraction for its valence electrons, and because there's a weakened attraction, the valence electrons are able to spread away, are able to move away from the nucleus more than they were with argon. Or if you were going to answer this question from argon's perspective, argon's valence electrons would be pulled more tightly to the nucleus due to that increased attraction. Why does S have a smaller electron affinity than chlorine? S and Cl are in the same period, so they have the same amount of shielding, but sulfur has fewer protons than chlorine. Electron affinity is the ability to gain electrons, to release energy when you are gaining electrons. When you have more protons, if you have the same amount of shielding, when you have more protons, you have a greater nuclear charge, which is going to result in a greater attraction for those valence electrons than you would if you have a smaller effective nuclear charge. With that in mind, because chlorine is able to hold on to its valence electrons more tightly, it knows what orbitals, how many orbitals are shy electrons of having a filled valence shell, and chlorine would be 1 shy, while sulfur would be 2. So adding 1 electron to sulfur's valence shell is not going to result in a filled energy level. It's not going to be as stable as chlorine's would if it gains that electron. Remember, filled half sublevels or completely filled energy levels are your more stable electron configurations. So by having that valence shell closer to the nucleus with chlorine, due to its increased nuclear charge, additional energy is more likely to be released to gain an electron, and in the case of chlorine, fill its energy level. Why does nitrogen have a greater ionization energy than phosphorus? These two are in different energy levels. Nitrogen has 1 filled energy level, phosphorus has 2. So phosphorus has more shielding than nitrogen. They both are in the same group. They have the same number of valence electrons. Because there is less shielding with nitrogen, the nucleus is going to be more attracted for its valence electrons compared to phosphorus. And since there is less shielding and that nucleus is more attracted to those valence electrons, it's going to require more energy for an electron to be removed. So the closer you are to the nucleus, the more energy is going to be involved, be it endothermic or exothermic. Endothermic for ionization, exothermic for electron affinity. Why is Br minus bigger than Rb plus? These are isoelectronic ions. They both have 36 electrons, but bromine has 2 fewer protons than Rb does as an ion. They both have a filled valence shell, but because bromine has a decreased effective nuclear charge, it's not going to have as strong of an attraction for its electrons as rubidium ions are, and therefore that weakened attraction is going to reduce the attraction for the nucleus for those valence electrons and allow the distance to increase. And that would be the end of periodic trends.